some of the dullest stuff in all of physical chemistry, organic chemistry, but however, most of what I'll be talking about today and tomorrow probably is pretty familiar to you if you had any chemistry anywhere, because this is the kind of stuff you love to teach. There's more to read there. So I won't feel too guilty, and I will go over it pretty quickly. Alright, so then general change in state. You write A moles of A, specify its state, and B moles of B, specify its state. Any other things that are there. C moles of C, specify its state, plus D moles of D, specify its state. Plus this other product you are, and then have some constraints out here. And our constraints will usually be pressure and temperature, but they could be other things as well.
Now, supposed to be the derivative? Yeah, you were saying this C is supposed to have
D
the
moles
derivative.
of D.
But C moles of C. Is that called apostrophe derivative?
No.
No.
Well, I'm going to consult the equation. We have the heat of the reaction, which is Q of P, as we've already learned, is equal to C moles of C plus, excuse me, C moles of HC. I'm going to borrow that. This is partial molar enthalpy of C if it's your substance, it's the molar value. If it's an ideal gas, it's a molar value. If it's an ideal gas mixture, it's the molar, it's a partial molar value. If it's any pure substance, solid, liquid, or gas, it's the molar value. If it's a homogeneous mixture, a solution, it probably is something else that we learned with the alcohol and water. Okay? Volumes, the same is true for enthalpies and radius and everything else. So I just write this out to be generically true. Plus D moles of the partial molar enthalpy of product B, which maybe it's molar enthalpy. And then minus A moles of the partial molar enthalpy of A, B moles of the partial molar enthalpy of B. And particularly that's delta H. Now I will use a shorthand notation. We write delta H or any other extensive state variable, we just change H for whatever it is, volume or heat capacity or whatever. I write it this as a summation of U sub I times HI bar, where U sub I is a mole number of species I in the Faust equation. And Ui is positive value of that mole number for all products, and negative for all reactants. So this notation says the same as that previous equation up there. And you might notice that if, perchance, we had, if perchance we knew all the partial molar enthalpies of all the reactants reactants products in any reaction you can dream of, so we can write down the heat reaction. And this same statement can be made for other property changes, some of which are rather more interesting. We will deal with them if we ever get to it. Not hurtful, that we will. Now, in my notes, I call that equation 1 up there. So, by this relation, we can write delta H is equal to, and just what this says, it says UC H R is C plus U P H R of P plus others minus U A times H R of P plus U V times H R of V plus this. If we rewrite this way, we do reactants this side, leaving the products on that side, transferring delta H, we get this result. U A times H bar A plus U B times H bar B is equal to U C times H bar C plus U B times H bar B minus delta H. All right. Now, if we compare that to equation 1, that's equation 2. If we compare that, we have here A moles of A plus B moles of B plus C moles of C plus D moles of D. Almost got a similarity here. We have a similarity. If we write out here minus delta H, then those equations are identical. That's equation 1 with delta H subtracted on the right hand side. These are the equivalent. If we designate that, if we designate that the chemical formula A in this equation represents partial molar enthalpy of H, partial molar enthalpy of H. B represents the partial molar enthalpy of B, etc. So you see those equations become identical. And in doing so, we can then read this as an enthalpy equation. Wait, we have this is that, this is that. These have negative signs. That's news. This is that, and there's a correspondence. Well, all right. A little fussy to do. This is not science, not teaching any science today. This is just all vocabulary. That's how we talk about this. So let's consider an example. I've got hydrogen gas plus a half mole of oxygen gas. If water, liquid, at some pressure and temperature. And that's 1 atmosphere, 25 degrees Celsius generally. Delta H of this reaction is measured calorimetrically, can be measured calorimetrically it is minus 285.83 kilojoules. Now, that's not kilojoules for bleeding mole, that's just kilojoules for reaction. You have to put the moles in when they belong and leave them out when they don't belong. All right. So why is it minus? Clearly, that's a combustion. We know that reaction gives off a lot of energy in the form of a heat flow to the surroundings. So why is that a minus?
Because it's formation. It's like the
Why is it
opposite.
minus? It could be a positive sign, it still represents heat formation. Except for what? What is heat flow in thermodynamics the way it's defined in your textbook in this course? It's heat flow to the system. Where the hell is this heat flowing?
Out.
It's around, so it's negative. Okay? Same as in work goes to the surroundings, it's negative. So when we see delta H has negative value, we know that's an exothermic process. All right. So the thermochemical equation then looks like this. H2 gas plus on that O2 gas, H2 coke, liquid, and then it is plus 285.83 kilojoules. And this is minus H. So every time we write a reaction down, an equation down, and put some number of energy units out here, that number is minus delta H if this is an enthalpy equation. It's minus delta G if that's gives us free energy equation. It's minus delta A if it's Helmholtz free energy equation. It's minus delta Cp as heat capacity. All right. This is an enthalpy equation. It could be over here, this could be minus delta V, it's a volume equation. It could be minus delta U, it's an energy equation. It could be minus delta Cp, it's a heat capacity equation. It could be minus delta G, it's a free energy equation. So that's the way we translate this language in this class. Now, most thermochemical data are recorded at some arbitrary standard, some reference pressure and temperature. And that varies from place to place and time to time in history. Usually 1 atmosphere or 1 bar. And the numbers are very slightly different. And I'm not going to quibble over that because that's nitpicking. And 25 degrees Celsius, which is 273.15 Kelvin.
Isn't that 298 Kelvin?
Yeah, of course. 298.15. I'd add that 25 on there. Thank you. So, okay. So how do you get numbers to put into to tabulations of data like this? have to do calorimetry, we've already talked about this. That measures delta H of reactions. So if I have reactants or products at some temperature, T1, and I do this in a calorimeter, if it's exothermic, we get products at temperature T2. This is delta H of the calorimeter is what it measures. This is minus delta H T1. And pretty clearly, thermodynamics says that how you go from state 1 to state 2 is in a path. So if we go by the direct path of the calorimeter, we measure delta H, which is minus delta H calorimeter. If we do it in our imaginations by having an isothermal process and then warming or cooling products, we have that delta H is equal to delta H T1 plus what? Plus the integral of the heat capacity of the products, constant pressure from T1 to T2. And the heat capacity of the products is just equal to the summation of summation Ui by Ni times the partial molar heat capacities from the species under this the products. So we have that relationship. We could also have gone this way and that way, and then we would have had delta H is equal to the integral from T1 to T2 of the heat capacity of the reactant plus delta H2 plus delta H T2. And you can put these together since they are equal and show that delta HT2 is equal to delta HT1 plus the integral of delta CP dt from T1 to T2. And that's the equation you use in calorimetry to get these reactions at some designated temperature. And we could arrive at that conclusion maybe less intuitively, but perhaps more simply. After reviewing these ideas, to recall that the partial derivative of H with respect to temperature at constant pressure is the heat capacity at constant pressure. And that the derivative of the enthalpy is then at constant pressure, which is equal to C sub P times the derivative of the temperature. Now, for the reaction, we have delta H is equal to summation of mu I H I R. So the derivative of delta H is a partial derivative of delta H with respect to temperature at constant pressure is a summation of mu I times a partial of H I R with respect to temperature at constant pressure. And that's just a summation of mu I. What's the name for that partial derivative? This is its vocabulary stuff. Partial of enthalpy with respect to temperature at constant pressure, it has a name. What?
Heat capacity?
Yes, heat capacity at constant pressure, I have a name right here.
Yeah.
This is generic, general. This is some specialized case. So it's C But one other thing, and what do we call this by our formula? We could call this delta CP. That's delta CP for that reaction. It's heat capacity of the products minus heat capacity of the reactants. Change the heat capacity of the system. State one state. So we have delta H then is equal to the integral of delta Cp dt right there. This from T1 to T2, this from T1 to T2, this is delta H T1 is equal to delta H T2 plus integral delta Cp dt T1 T2, which is the same equation. The way I show it to you first is sort of visual. You can sort of see that in the calorimetry. And this is just mathematical. You get the same. All right. So I said that if we know the partial molar enthalpies of substances, which might be the molar enthalpies if they're pure or ideal gases, if we know them, then we can calculate each reaction. How many reactions might be of interest to chemists all over the world in a lifetime? A whole hell of a lot, right? A whole hell of a lot. If we had to tabulate the thermodynamic data for all those reactions, it would be just mind-boggling. You don't have to do that. It's like how many sentences might one want to read or write or think of in a lifetime. It's a whole lot. How many, if you had to put all those in the book somewhere, it would be a mess. But if you got a dictionary and all the words, then you can create the sentences. Same thing here. We needed something like a dictionary tabulation of molar enthalpies, partial molar enthalpies, lots of different products, substances, which are our words, and then we can put them together in different ways to make sentences or reactions. So that's the plan. We cannot measure absolute enthalpies. Fine, because enthalpy is by definition energy plus ED product. We can measure absolute values of pressure and volume, so we can measure the PV product absolutely, but that energy we can't in thermodynamics. Other than to say, well, it's MC squared. Well, hell, we can't do chemistry by using the mass equivalence of energy. That's just not practical. So there's no absolute basis for this for practical purposes. Therefore, there's not for enthalpy. So if you can't measure absolute, what's the next best thing? Measure relative. So we're going to put together all these fabulous chemical equations, or sentences in a novel, or whatever, and we cannot expect to go look up the absolute enthalpies of all those words or all those compounds or substances. We want a set of substances to which we can assign arbitrary values and then make all the others wrong. So that means we have some arbitrary choices to make. How many is that? How many is that in chemistry? We want to make up all the things you can conceive of that we can make in our laboratories, the chemistry that we have available to us. How many arbitrary choices we make in setting these relative enthalpies. Well, if you look at that chart up there, you see everything you make has to be made out of those elements. Right? There may be others somewhere, there may be others that our physics students can make in momentary consistencies. But the ones in the laboratory, if you want to slop together, they got to come up with that chart. And there's 100%. And you got one arbitrary choice for each element. And you can choose each element in some state and assign it a value. Enthalpy, you say, I got that state. And then if that element is part of a compound somewhere, and all the other elements have values assigned to them, then you have a touch base. You can go back and figure out what its enthalpy is. So that's the spirit of it. That's the spirit. So the question is, how do we make this assignment? Well, we've got 100 or so elements, 100 or so choices. So, you know, you could say, well, we'll choose hydrogen. That's the first element. And it could be atomic hydrogen, or it could be solid hydrogen, or it could be liquid hydrogen. We would have some standard pressure, say 1 bar of atmosphere, probably H2. So we choose elemental H2 and say that's our standard. So it's element number 1, so we say it's standard enthalpy is 1 or 2. And helium then would be 2, lithium 3. So that'd be sort of stupid. Nobody's ever been thought to do it that way. What would be the logical choice? I'll make this choice. Each element in its most stable state at our standard pressure and standard temperature, which I'm just going to assume is 1 atmosphere, and 25 degrees substitute to 98 Kelvin. Left H. There's a squiggle now because this is pure. There's a 0 on it, meaning the standard state. And assign it a value. So what's the smart value to assign? There's no answer to this. It's always 0. That's the easiest one. There's no smart. It's 0. With an exception. For gases, like hydrogen, oxygen, so on, these are gases. The standard state is a hypothetical state. Is the pure gas at E0 and E0 the ideal gas state. In other words, it is that gas when you turn off all the molecular forces. You say you can't do that. You can do it in your imagination, and that's where it's done. Now, why would we do that? We do that because we got lots of really useful information, thermodynamic information about molecules from studying the spectrum of gas molecules and interpreting them with quantum mechanics. And that always, those interpretations are always based on individual molecules, not on clusters of them around. it's easier to, refer gases to that idealized state and then make the corrections for non-ideality on an as-needed basis than it is to, tabulate the properties for the real gases and within the regular course is all active. And then have to deal with them each time someone does an experiment that shows measures better. Nonetheless, that's what it is. So already then, we're trying to make a cake. We're going to list substances, we're going to have standard, molar, enthalpy. Standard partial molar enthalpy. And we want to put values in there. We've already got 100 values, you see. We've got a value for every element. But that's can't do much chemistry with that. So we need to advance. So let's see what some of these values are. So we've got substance. Right now, we're not going to have any constituents in solution. We will in time, but right now they're pure. So we just have lower enthalpy. And these are elements. So there'll be hydrogen, gas. If we understand that this is the ideal gas, the value is 0. And we have helium, gas, and 0. Oxygen gas, 0. Nitrogen gas, 0, etc. Well, we got lithium as a solid is 0. And CO2 is a gas, it's 0. How about bromine? What's the standard state of bromine?
0.
Hmm?
0.
It's a liquid.
Oh, standard state. Sorry. Answer
I'm
was
saying
wrong.
which values, in what state do these things get assigned values? Yeah, iron, it's a salt, 0. And you go on nozzle, mercury, it's a liquid, 0. Sulfur, ooh, wow. What do we got here? Sulfur, standard state of it is a solid. It's actually an SA, molecular solid, and 0. Phosphorus, C4, solid, and it's 0. And so on. All right. Now, a consequence of these choices is that H0 for any other state or molecular proposition is H0 of the substance is equal to delta H0 formation of 1 mole of the substance standard heat formation. Its elements each in its standard state of 0 enthalpy. That tells us how we go about getting non-elemental contributions in here. So let's consider. course, it's standard state heat conditions. And we got plus 285. 0.83 kilojoules at our P0 and T0. So by definition, using our shorthand notation, delta H for this process, which is equal to H0 of liquid water. We'll get more careful. Remember, delta H is equal to summation of UI, HI bars, or these are motor values here. Gases are ideal, and waters of your substance. So, we write it out. It's equal to 1 mole times standard molar enthalpy of water minus 1 mole times standard molar enthalpy of hydrogen gas minus 1/2 mole times the standard molar enthalpy of oxygen gas. Or, write it out one time. R H0 of water is equal to delta H. And this is a formation of 1 mole, so this is the delta H0 formation. Plus 1 mole H0 hydrogen plus 1/2 mole H0 oxygen. We'll divide this by mole. That one there, and we get that it is equal to delta H. See, we're not put a squiggle on this, it's a molar formation. Plus what? Plus 0 plus 0. Why? These are standard states of values. 0. That just verifies what we wrote in this previous page. That the standard molar enthalpy of a substance is the molar enthalpy of formation of its elements in your standard state conditions. Let's test it. So you can take that bank and use that to find out the value. All right. So we get from this then that what is that value? Well, right, we got 285.83 kilojoules per mole. How about the sign? Is it plus or is it minus? All you have to do is look at the equation. So we're plus 285 because we know it's an exothermic process anyway. So what's delta H? It grieves me to see on rare occasions when students screw up on tests and exams by getting the wrong sign. Usually you can do it intuitively, you can see, but sometimes they're not so obvious. Have to be methodical about it, and that's why people love to teach this stuff, because there's all sorts of literature students are home tests. All right, so what's that? That's an entry in our table. Now we got H2O liquid minus 285.83 kilojoules per mole. That's the first one. What did the calorimeter measure when it measured this? It measured combustion of the real gas hydrogen, real gas oxygen, not the ideal gases. So should this be corrected for parts of not ideal? The answer is yes. But those corrections, it is complete. We're not going to. Let's look at a case where it's not calorimeter. Calorimetric, there's one measure was corrected for the non-ideality of gases hydrogen and oxygen. Let's get an idea how big that correction is. Let's do this by considering is it more departed from an ideal gas state at standard conditions are about the same as hydrogen oxygen?
More.
Yeah, sure. We know it's easier to liquefy it into a solid and all these things. So, which is more non-ideal than hydrogen and oxygen. We play the same game with that. In this exercise, so we still left P0 being 1 atmosphere, temperature 25 degrees Celsius, and we'll have a pressure which I call P star, a low pressure, at which carbon dioxide is very nearly near as you want to be ideal. So we're not having 1 atmosphere, but carbon dioxide is not ideal, and we're going to take it somewhere at a real low pressure where non-ideality is negative. And so we have P star is much less P0. We don't have to state what that is, because we'll assume it goes to P star goes to 0. All right. Here we got carbon. Graphite is the standard state. Carbon, not diamond, not buckyballs, and not graphene, not a lot of things. This is standard state. Plus oxygen, which I've already said, the correction out for non-ideality is a negative one. CO2 gas plus 393.55 kilojoules at our P0 and P0. What's the name for this right here? This is minus delta H combustion. Because that's a burning, we burn some graphite. All right. Now, we're going to look at some other changes. We'll start with graphite. We'll start with graphite. Fine with graphite. We're going to take the carbon dioxide gas, we'll call it a real gas. P0, then we'll take it to like this, carbon dioxide, real gas at some very low pressure, and minus delta H T. This is just temperature T0. So I lower the pressure of the gas isothermally. Then I'm going to take CO2 real gas Then I'm gonna take that low pressure CO2 ideal gas, that P star, and I'm gonna compress it. Ideal gas, P0, on still page 4. It's just and then I'm gonna sum all these up. See, a lot of things gonna cancel out. We'll wind up with carbon graphite plus oxygen gas, ideal gas we've already decided it's good enough. Goes to what? Goes to CO2 ideal gas. And put a T0, T0 minus delta H net. The delta H net is equal to delta H combustion plus delta H plus delta H3 plus delta H4. Alright. Delta H combustion is that number minus 393.55 kilojoules. Delta H2, now look at this, what do we got? It's constant temperature process, it's expanded gas. Looks to me like it has to be partial derivative of the enthalpy with respect to the pressure at constant temperature times dP, and integral of that D0, D star. That's just putting in mathematical notation what you take cast out. Wow. We've studied this partial derivative before. Anybody remember what it is? Laid a chain rule on that you have minus integral D0 D of the partial H respect to temperature at constant pressure over the partial pressure respect to temperature at constant H. Constant D. Remember the chain rule? So we don't need it. First time it's actually needed. But that is minus integral G0 stuff right here. All right, what's this? What's this partial derivative here in the numerator? You must get where you recognize that right away. Right away. See? What system? Well, we don't know what it is. So if you turn it upside down, it's partial. We put it in the numerator, partial temperature, respect to pressure, content enthalpy. That has a name. What is it? It's a Joule-Thomson coefficient. So it's a reciprocal Joule-Thomson coefficient. No, this is the reciprocal Joule-Thomson coefficient. So you have minus Cp times UJP times or I write it as minus integral P0 P star of NCP molar times UJP times Cp. All right. N is 1 mole, heat capacity, lower heat capacity of carbon dioxide is measured quantity, I'll write numbers in a minute. The Joule-Thomson coefficient for carbon dioxide is a measured quantity, at this, temperature. So write all those in, calculate this first. So we have delta H2 is equal to minus, the heat capacity is, first I got 1 mole, then the heat capacity is 37.11